The broadcast is now starting. All attendees are in listen-only mode.
Yeah, we ordered I don't know, we ordered something a few weeks ago, and then they were like, "Oh, well, our factory is doing well, and except that we had an earthquake and the headquarters was um disrupted." And it's like, "Oh, okay, well, that's exciting."
Yeah.
Oh man,
I was going to wonder what's next, locusts, but
I
then I guess that
pretty
already
much
happened in,
I
I think in Africa we already had this. Just give me a sec. I'll be back in just 1 minute here.
sure.
All right.
All right. Well, it's 2 o'clock, everybody. We'll give people a few more minutes to join us. In the chat, I have placed a link for the files for today. So today is going to be the odd man out as far as files go. We will be using, or we'll be creating, a Jupyter notebook at the end of this afternoon. But we're actually going to be talking mostly concepts, and so I think this will be the only PowerPoint slide set you see this entire seminar series. And so if you're interested in downloading them, you can download them from the Python_biologist repository that can be found at my GitHub. And then that will also be uploaded and archived at the NIAID Bioinformatics portal. And then we're also going to try and make this a little bit more interactive. And there's a link to a poll that if you'd like to join, and then we'll be using that through today. All right. Somebody's saying that they can't see the chat box. It should be in the GoToWebinar control panel. That usually pops up on my screen, at least it pops up over to the right-hand side. And if you can see that, it's the very last option that is has a dark gray header. So if you all can see my screen, this is what the GoToWebinar control panel looks like. And here on the bottom is a chat option. I will pull it down so that you can see. And so the poll is just at pollev.com/NIAID, N-I-A-I-D, Python, one word. Okay, and so it seems like things have leveled off a little bit. I'm going to go ahead and get started. Welcome, everybody. Let's figure out where that little window goes. Okay. And let's just take a quick look here. Nope. Let's go to desktop. So if you all joined us on Monday, I would say welcome back. And if you weren't able to join us on Monday, then welcome. My name is Burke Squires. I'm a computational biologist with NIAID's Bioinformatics and Computational Biosciences branch. And these are some webinars that we have, I would say I've traditionally taught through CIT on campus, but obviously we're not able to do that now. These talks are being recorded. Right? This is a series of 10 talks or 10 seminars, and this is our second seminar. And in looking at the poll, I want to remind people that this is in large part a seminar that's meant for those who have little to no programming experience. And so the concepts, we're going to be talking about concepts today, and so I would welcome anybody to join, of course, but I would say, well, with regards to questions, we'll try and focus more on the questions that are a little bit more basic, and then if we have a chance, we can address the rest of them. Okay, and these materials and then the video will be uploaded and archived at the NIAID Bioinformatics portal, and that is at bioinformatics.niaid.nih.gov. And I want to thank my colleague, Brendan Jeffries, for joining us again. Actually out of RML. He is another of our computational biologists. And so what we're going to be doing today is talking about beginning or concepts in programming. For those who may be interested in following along, I would say this is the one rare case where I'm going to be using a PowerPoint presentation. And so if you would like to download that to look through it or to reference it later, you can do that. At this point, the materials are on my GitHub website. It's in a repository. So if you go to github.com, GITHUB.com, and it's in the chat. My username is Burke Squires, and then the repository is the Python_biologist. And so if you click on the home page, you can see that it's the first pinned repository. And we're going to be looking at this 03 Intro to Programming. And you can either click the download option here and download the zip. That's a larger download that includes all of the different materials. Or if you want just the materials for today, you can click on the zip archive folder. And then you'll see that was uploaded recently. And it's the 03_intro_programming. Okay. And so if you've also just joined us, then please feel free to input. We're going to try and make this more interactive. I recalled on Wednesday that doing strict webinars is more difficult because there's less feedback from you all than normally in the CIT classroom that I will give these. And so this is one way to hopefully engage and then give us each some input. All right, and so we can see that there are roughly 60% who have not programmed before. And I'm going to give you a kind of a lead in here, and I say that I suspect that you have in fact programmed before. It may not have just been obvious programming. All right, and then those who have programmed before. Okay. Let's see. So we're going to pop over to our wonderful little PowerPoint. Right. And so why attend this seminar series at all? And I would say, especially for people who have not programmed before, that is not an obvious question, right? So why should you learn to program, right? Why do we have to program, right, a computer? Why should somebody learn Python? And so I hope that, say, today we'll answer some of that, if not all of it, and then certainly through this seminar series, we will answer all these questions. And not only that, but we'll answer even the hows, right? How can programming help you? How does one program a computer, right? And then how can you learn more? And so what I hope you will get out of today is the ability to compare very briefly, right, some hardware, software, and programming languages, how to communicate better with programmers and bioinformaticians, how to convert what we call pseudocode to actual source code, and hopefully, as I mentioned on Monday, right, that we're going to be in part recognizing that a huge advantage of programming is the ability to make our research more reproducible. Ultimately, I hope to enable you, right, to see differently, and that when a program might be useful, and then help you to think more clearly. Okay. So why would somebody program? Right? In essence, that comes down to, right, in large part, right, we work, we want to be able to, right, do our job, do it well. And so, right, what are some examples with regards to why program, about how programming can help us? These are just some examples, right, of what a program will do for us, right? It helps us to rerun an entire analysis, right, on new data almost instantly. Programming can help us glue output from one program, right, to the input of another program into a single workflow. We can test multiple parameters all at the same time. We can download data from a known location and process it automatically. We can create, update, move, or rename files and folders easily, even if there are thousands of them. We can also program and use it to create a web portal or a graphical user interface for our software. In large part, as the title of a book I will be referring to is, programming helps us to automate the boring stuff. So more specifically from a research perspective, right, why do I think that you should learn to program? In programming, you learn to do your job faster, right? And so this is where we repeat that analysis, right, just by replacing the input. we can do our analysis better, right? If I'm using some statistics in my software that will help me, right, validate my analysis. As we've talked, right, we can make our research more reproducible. And then ultimately, right, this is also about becoming more competitive, right? Many researchers know how to program or are learning how to program. And so, right, the bar is changing. Okay. Now, I will be the first to tell you that there are many advantages to programming, but I also want to perhaps be the first to tell you that there are also challenges to programming. Okay. And so some of those challenges that we'll be talking about a little bit today, the first one is, right, picking a programming language. I would say in part, that is kind of taken care of in the sense that you are learning, right, how to program in Python. Learning a programming language, well, you are already, right, working towards getting over this challenge by taking this seminar series. Knowing which piece of the language to use, that is something that the exposure of this seminar series will help, right? But it will certainly not teach you everything that you will ever need to know. Debugging is perhaps the greatest challenge of programming, right? And what that really means is making the program work and then making it do what you intended it to do, but perhaps what it is not doing yet. Some of the other challenges include remembering what a program does when you come back to it, keeping track of different programs, and then there is the challenge of, right, not practicing. So you can take this entire seminar series, and if you don't practice, right, then you won't necessarily retain much of what you've learned. So as I said, I suspect that many of you have programmed before, but may not know it. So have you written a formula in Excel, right? Or have you recorded a macro in Excel? Right? So let's pop over for a minute and let's see. So it looks like we see that there are, right, about 55% of us who have said that they have not programmed before. Okay. Let's see. Let's go to a new question. Try to go to a new question. Well, so let's see how many of you have written an Excel formula. And by that, I mean used something on the order of so for those of you who may not, right, so writing an Excel formula just means that you type in a cell, right, the equal sign, and then most often there is a right, a parenthesis, and then you type in some type of information. Okay. So as I suspected, right, the vast majority of you have, right, written an Excel formula, and so that is a form of programming, right? It isn't natural or inherent for us to type that equal sign, but that is how we make Excel, right, do what we want. Thank you all. This is great to have that kind of feedback. Okay. All right, so let's talk about for a minute, right, why we need to program, right? So think about for a minute, right, what are the differences, right? Or the similarities, but let's start with the differences. I'm sorry, let's start with the similarities between these two computers that we see before us, right? We have a laptop over on the left-hand side, and we have what is affectionately known as a supercomputer, right, over on the right-hand side. Okay. What type of, what are the similarities or between these two? I'm going to go to a next question here. Oh, wait. Well, let's go back to polls. And I want to create and actually we're going to make this one open-ended. Right, so what are the similarities, right, between the two different computers? Right, so we have just a laptop and a supercomputer. Now I'm going to give you a few hints here, and I'm just going to tell you that, right, this is actually also called, right, a high performance computer, as you can see, or it's known as a compute cluster. Okay. They certainly use digital information. They both have processing capabilities. They definitely have, yep, hard drives and processors and CPUs, right? Our CPU is the same thing as a processor. They perform calculations. Okay. So in addition to the, or in contrast then to the similarities, let's not necessarily change the question here, right? What are the differences between these two? Okay, so I'm going to try, let's look at, right? Okay, so there's some, so they have different power and speed and then different functionality. All right. Let me try creating a new one here, and let's look at, okay, so here, let's go ahead and make a different question. That way people can enter their answers. One is big and one is little. Yes. All right, a number of processors is definitely different. The big one is definitely more user-friendly. All right. Well, so I think as you all can see, right, we understand that there are, right, similarities, right, and differences between the two of these. Now, what is rather interesting is, decades ago, when you talked about a supercomputer, it was vastly different than what somebody would use, right, on their desktop. Now, that isn't necessarily the case, right? So this compute cluster is a collection, right, as we can see, of a bunch of essentially commodity server computers that have, in many cases, very similar processors, right, except that they just have more cores in them. right? But I would say there are perhaps more similarities than we initially, right, attribute to the two of these. Okay. With regards to those similarities, right, and right, we're trying to answer, right, why do we need to program? Right? We understand that computers, right, they work on electrical impulses, right? That means that they communicate via a bit, right, which is short for a binary digit, right, a 1 or 0. Those ones or zeros are collected in groups of 8s, right, called a byte. And then we'll also, although it's not as often that we hear it, right, the computers also communicate in words, which is kind of the path that goes through the CPU. And so when we talk about a 64-bit piece of software, right, that is the word size that it talks about at a particular time. All right, that's great, but Burke, why should we care, right? What does that mean for us? So ultimately, what that means is that the way that we speak, whether we speak in English or French or Chinese, right, is not the same way that a computer speaks, okay? And so we also have different ways of getting at, right, computers. So computers talk in that 1 and 0. That is what's known as an assembly language. And the languages that we use, specifically Python, are what are called higher level languages, right? They're much closer to the English language than an assembly language, right? And so one of the things that I think is helpful to understand is the difference between an interpreted language, which is what Python is, and what R is, as well as, say, JavaScript, right, PHP and Ruby, right, and a compiled language, which examples include, right, C, C++, and Java. Okay, so there are, right, use cases and niches for each of these. For instance, none of us wants to use a Microsoft Word or use a Mac OS that is written in an interpreted language. It would be way too slow to actually use the computer. So those are written, or they're written as compiled pieces of software, right? The challenge with compiling is that it takes time to compile or to link everything together. And then when that compilation is done, a binary file is created that is local to a specific hardware. Okay? You'll notice over here in the interpreted version that there is this quote unquote virtual machine, right? The interpreting that goes on. And so we are learning Python because it allows us to quickly write software, and we can take that software and then we can run it on our laptop as we saw in the picture, right? Or we can take it and run it on a cluster without, or I would say with minimal, right, changes to our code, right? And so we're going to be using and working with interpreted code. It is inherently a little slower, right, than compiled code, but as we will see in this seminar series, that programmers, right, within the Python world have found ways to get around that slowness by, in part, right, writing some of the software that we're going to use in the language C, and then they tie it to a Python interface, and then that is what we interact with. And so I'm thinking specifically of the NumPy, or the numerical Pi package, that we'll be talking about in the data analysis seminar. Right? So the take-home message here is that we are going to write stuff, right? We're going to write our program in an interpreted language, and then that is, right, converted or interpreted to something that the machine can run. And so here we see, right, a very, very simplistic example of, right, a compiled code for C++, and a compiled program, excuse me, I'm sorry, an uncompiled, it's just the source code for C++ and Java, plus Python and R for the simplest program, what's called the Hello World program, where you want to print out the words Hello World to the screen. And so we can see that there is, right, some additional setup, right, and information that's required in C++ and Java that is not required, right, in Python or R. Okay, so now you all are totally convinced, right, that we have to write software, right? And so we're going to use, right, the Python programming language to do this. But now the question is, right, how do we do this, right? And so somebody is asking online, how does something like Unix fall into those categories? So Unix, as Brandon, thank you, is an operating system. And so Unix is written, or is compiled, right, just like the Mac OS or Windows OS. And so all, I would say, operating systems, right, are compiled, or the majority of operating systems are going to be compiled, and that is going to allow them to run as absolutely fast as possible on the hardware that they're on. And then something like Microsoft Word, right, or Adobe Photoshop will also be a compiled piece of software, right, because once again, you want it to run as fast as possible. But with our, right, scientific scripts or our Python programs, we are, right, normally most interested in being able to write something quickly, right, test it quickly, and then iterate very quickly. And Python allows us to do that as an interpreted language. And then when we combine it with something like NumPy, as we'll see, then we can actually get, right, the best of both worlds. And so yes, DOS is also going to be compiled. Right, good question, y'all. All right, so we know that, right, we speak in English or some type of other, right, human language. We need to be able to get that from that language to, right, the ones and zeros that the computer understands. And the way that we do that is we write programs, right? So here, right, how do we write a program? So we think about, right, what our workflow or what kind of task we want to do, right? And as we'll see, what we're ultimately going to do is we're going to start by writing pseudocode, okay? And then towards the end of this afternoon, we're going to create pseudocode for a fairly simple task, and then we're going to walk through how we convert that pseudocode to actual Python code, right? To design our, right, program, or in essence our algorithm, we write our pseudocode, and what this really means is that we're going to break down our tasks, right, into smaller tasks. We're going to, right, we're going to describe each of the major components of our software, right, as each of these smaller tasks. Now this may sound difficult, okay, but let's look at an example of a process that I think most of us are familiar with, right? So let's find out how many people have ever made, right, a cup of coffee before. Now, at one point, I thought I read that scientists drink more coffee than anybody else in the world, and so I'm hoping that the answers are largely yes, right? And so if we think about, right, a workflow, right, we're alluding to, or we're working up to the idea of an algorithm here. Who drinks coffee, right? Have you ever made, right, a cup or a pot of coffee? And it is no coincidence that the picture here is of a French press coffee maker. Somehow, some years ago, this seemed to be the coffee maker that was available here in our house, and so I have been making French press coffee since then. Let's see, so it looks like many people, right, have made coffee before, right? And so if we think about, right, what does it take to make coffee, right? Think about for a minute, what are the steps to make a cup of coffee or make a pot of coffee? And as you're thinking through those steps, consider whether, right, order is important. So we can see that, right, the majority of us have in fact, right, made coffee before. And let's find out if um, so do you think that order is important? I would like to talk to the individual who might answer no to this. Right, and so, right, when we think about making a cup of coffee, if I use the French press example here, when I make a cup of coffee, I will heat up some water. I will put some coffee grounds in the bottom. Once the water is boiling, then I will add that to the French press, and then I happen to stir it. I don't know if it necessarily makes any difference, but something seems to tell me it does, or I think it does. And then I put the lid on, and I push it down, and then I enjoy my cup of coffee. Right? And so if I were to change those steps, so even if I had all of the right steps, if I perform them in the wrong order, which, it's morning when I'm drinking coffee, there have been times when I have put cold water on my coffee grounds and had to essentially start the process over. So the order is important, right? So when we're thinking about programming, we want to get the right steps, right, and then put them in the right order. Okay? Now, for your entertainment, I think this has got to be one of the most challenging recipes or algorithms for making coffee. Right? So this is a rather interesting example of an AeroPress, and in this graphic they have gone through and showed us the 12 different steps to make AeroPress coffee. And so I would say for those of you who are scientists, this looks very familiar in the sense that this is a protocol. And for those who may not be scientists, but you recognize this could be essentially be a flow chart or a recipe, right? And so something that we're very familiar with. Right? Now, what happens if I wanted to take what came out of my coffee maker or the espresso maker, and I wanted to make these different coffees that are shown here? They all begin with that initial product of coffee, but what would be different about each of the recipes? What would be the same about the different recipes? And then what's rather interesting to think about, is reproducibility important? I suspect that if you ask people when they are receiving their Starbucks order, right? If reproducibility is important, they would say yes, that it is, right, with regards to coffee. Okay. What is very interesting, in my opinion, with this particular graphic is the fact that while all of these start with the same, right, input, right, the coffee itself, these are all, right, iterations on that recipe. And so if I do a good job of programming my algorithm to make coffee, then we can see that that can be used, right? I could take that algorithm and then slightly extend it in a number of different ways and look at all of the tasty, right, items that can be produced. Okay? And so, yeah, somebody's asking about some differences between Python and R, and we can talk about that a little bit later. And then part of that we'll also cover in our next iteration when we go through more of the Python language itself. But that's a great question. Okay, okay, so with regards to programming, right, what we are really interested in is we have some type of input, right? We want some type of output, and then there is this large black box, right, that's supposed to take us from our input, right, to our output, right? That is our algorithm, and that is going to be our Python script. Okay? Ultimately, what I want you to take away from today and then the rest of the series is a new way of looking at the world. And so what we're really talking about is a new way of looking at different problems. Right? It does not make sense, right, in my oh so humble opinion, to write a program, right, in Python or any other language for a task you will only ever perform once that doesn't take an infinite amount of time. Okay, so if you have to do something, even if it's on the computer and there is no conceivable way that it would be repeated, that is not a good option, right, for writing a script. But where in your work do you see repetition? Right? So let's look. So where in your work do you see repetition? And then in this case, it's really repetition that a Python script could help with. So repetition meaning, dirty dishes, that's going to be harder for Python to solve, right? I so yeah, the pipetting, that may have to wait until the next series. But these are excellent. So yes, so data analysis, right, gating of flow cytometry data, right, image processing, formatting of graphs, counting cells. Data entry, absolutely. And so can others think, now these are all, right, they're all great answers. And especially if, right, some of this comes from, right, your everyday work. What I also want to, right, make you aware of is that, right, there are some things that may not be as obvious. And so the response there of, say, querying websites, right, if I would say if we're looking at like the coronavirus data, right, in many cases, right, that data is available on GitHub. It's easy to download and to plot. In most cases, that's not the case, right? So it's possible that some data is put up on a website, but that website or that data is not, right, available in a nice, pretty format. But I can write a Python script, right, to, right, retrieve that data and then process it without having to manually, right, download it. These are great. Very cool. All right. All right, so right here, what I hope you take home is the ability to, right, see repetition, right, in your work. And then, right, this is, right, an option or an opportunity for reproducibility. And then there is this concept of the reuse of code. And so when we think about that, the coffee example and that last image where we had all the different types of coffee, right, I can reuse my code, right, if it actually existed for making the initial coffee, and then enhance it, right, with the products at the end. So I can add right, cream or milk or foam, right, or cocoa or something, and I can have, right, different coffee products. All right, so we've talked about a little bit of why a computer needs to be programmed. Right, we've talked about, right, how to at least begin to think about programming. Ultimately, right, why then should we learn Python as compared to many other languages out there? Right? So I'm going to read this stuff out to you, but I hope that over the course of these 10 seminars that you will gain experience with each of these. Right? So Python is a general purpose, right, high-level language. As we saw a moment ago, right, that means that we can write in almost English as opposed to having to write in the ones and zeros. Right? Let me know if the audio is gone. That's weird. Can you all hear me? Okay. I am so sorry. I will be more careful and get a little bit closer to the microphone. Thank you all for letting me know. Okay. All right. So in addition, or Python is it's a general purpose, high-level language. It is cross-platform and open source. It is an interpreted language, as we saw, so there's no need to compile it. As we'll see, the language is easy to read. It is very powerful. It can be very fast, right, especially in many of the use cases that we're going to be using. Python is described as being what's called batteries included, and right, that is a reference to, right, toys that we would have or get as a child that required batteries but didn't come with them. There is so much included in the Python standard library that it is regarded as being batteries included. Python also comes with a great community, right? And so what that means is that there are a number of packages that are available. That means there's also lots of help and tutorial. And Diana is asking about source code or open source. So open source, great question. What that means is that the source code for the language is available for us to look at. And so if I contrast Python to something like MATLAB or Mathematica, or even Microsoft Word, right? If I have a problem with Microsoft Word or with my program in MATLAB, then I can try and debug it. If I'm sure that the error is not right with my program, that is a bug in the software itself, I have to email the company and report the bug and hope at some point in the future that that bug is fixed. With Python, right, and with R and all other open source softwares, if I discover a bug, I can jump into the source code, I can look at that source code and perhaps, right, figure out why that bug is happening. And then if I understand, right, enough about what is happening, right, I can submit a fix to the Python, right, programming language, or to the Linux operating system, right, or any of these other open source projects. But from my perspective, right, I could potentially fix that the same day, right, that I have that problem. Where with a closed source program, that means it is closed to my viewing, I could not do that, right? And then what's rather interesting here to think that when we are working in these softwares, if we find a bug and we delve into it enough, the odds are that you may be now, right, one of the world's experts in that particular piece of code. And so then that gives you an opportunity, right, to fix it where others may not understand, right, what the problem is. Okay. And then additionally, right, reasons to learn Python. The software, right, is easy to install, as we saw with the Anaconda distribution. Right? And then it's also popular, right, for data science. Okay. And so from a, right, those are in large part, right, why Python is popular for, say, general usage. If we think about, right, what are reasons to use it from a scientific perspective, there are a number of different Python packages, right? This is source code that other groups or people have written that are made freely available for us to use. And so this first one, this NumPy, right, that is the package that I've talked about that does a lot of matrix, right, calculations within Python programs. And that is the one that I've referred to before, and that is written in large part in C, but all of its connections are using Python. And so it is, right, essentially it's a Python program, but the important parts are written in C, so that makes it very fast. On top of that, or built on top of that, is the Pandas package, which we will use to do some scientific data analysis. There are a number of different plotting libraries. Matplotlib is one of them. There is an Altair package. These are packages for, say, static plotting. We can also use something like Bokeh for interactive plotting or dynamic plotting. There's packages such as SageMath that allow us to do linear algebra, right, combinatorics, or calculus. SciPy is a large library of various scientific tools. Scikit-learn is a package that allows us to do machine learning, which we will cover later in the seminar series. If you want to do, right, some statistical analysis, there is the stats model package. And then, as we've seen, right, there is the Jupyter, right, package, and then the Conda or the Bioconda, right, components as well. Okay, but this is not, right, this last option is not actually a Python package, right? That is something that helps us to install Python packages. Let's see. And so then, is Anaconda compiled? I think it is, and then what actually Anaconda allows us to do is it allows us to install the binary versions of the files on our computer. And so that what makes it, so it does the compilation on their servers and then makes it quick and easy to, right, copy it to our computers. All right, with regards to, right, why perhaps, right, learn Python, I would be the first person to tell you that to use the best tool for the job. Right? And so as I mentioned, in some cases, it makes most sense to write in C or C++ or C#, right? If you want to right, work on the Windows operating system or Adobe Photoshop. But I think for many of the tasks that scientists or people, right, associated with, say, biomedicine are using, right, Python is and perhaps the best resource. And so we can see here that this is information, and it's taken from the, what is it, the Popularity of Programming Languages website. I think it's by, is it Tiobe, T-I-O-B-E? And this was captured earlier today. And so we can see that as of March, right, 2020, that Python is the most popular programming language, right, from their measurements. And then you can see over here to the right, for the longest time, right, Java was the most popular language, and that is in large part because, right, websites are written in Java, phone programs, right, are written in Java, and so much of the world, right, the outside world uses Java. But you can see that only recently has Python overtaken it, right, as far as popularity goes. Now we've talked about, right, a number of different languages. Even though there are these different languages, the concepts that these languages have, right, are shared amongst them all, right, with, say, a few exceptions, okay? And so all programming languages, right, have some way to represent data, and this is data from a very generic perspective, right? So we have integer data, we have floating point data, Boolean data, right? So not all languages have a way to represent Boolean, right, as true or false. In many cases, they would pseudo represent it as being a 1 or 0, okay? Programming languages have the options to represent characters or strings. And then in addition to those basic, right, data types, there are also what are called data structures. And so data structures can include what we would, I would say, traditionally, or from a computer science perspective, talk about as an array. From a Python perspective, this is known as a list. And I've tried to give you some idea of how these differ. So an array, it is ordered, duplicates are allowed, right? And I can change this once it is created. So this is an example in Python. I have a list here of 3 letters, I mean 3 numbers and then 3 letters. I can mix this up, okay? A tuple, right, is very similar in the sense that it is ordered, duplicates are allowed, but once a tuple is created, it cannot be changed. I would say this is, it has, I think it has its uses, but I would say it's not something that I use all the time, okay? Melissa is asking if programming languages are case sensitive, and I want to say that the majority of them are. I know that Python is, and so if I create a variable, if it's all lowercase or all uppercase, that would be different. Okay, good question. In data structures, we also have sets. And so in this case, a set is going to be unordered, where no duplicates are allowed. Okay. And then we also have, what is it called? Like mapping data types or data structures. And so this is, from a computer science perspective, is usually referred to as a hash. And these are, right, key value pairs. And so in this case, if we were to use the gene symbol BRCA1, right, we would link that to a particular description, say of a cancer gene. Now this, in the Python parlance, is a dictionary. These are unordered for the most part, right? The Python language has actually changed to allow us to order it, but for the most part, it is unordered. There can be no duplication in the keys, which is this element here, right? The gene symbol in our case. But you can have duplication in the values themselves. And then, of course, these can change, right? We can add or subtract to a dictionary over time. Okay? Once you have your basic data, right, elements or data types and your data structures, then we get to elements in a programming language that help us to write that language, right? In this case, we need somewhere, right, to store information, right? Either the values we read in from a file or the file name, and that we do in something called a variable. Right? A variable is it has three specific parts, so there's a value to it, right? And then that it has a name, right? A value, and then it stores in a place in memory, right? And so if we look at this example down here, if I have a concentration, and the concentration is 10, right, micromolar, okay, I would name my variable to be CONC, perhaps. I would set it equal to a particular value, and then ultimately this value is stored right somewhere in my computer, and the variable is what helps the computer keep track of it. Right? That means I don't have to remember where in memory it is. Right? And that's one of the benefits of using a high-level language. Now, we will go over variables and how to name them in our next session, but one of the things that we need to understand from say, a general use perspective is that I can make variable names almost anything I want, with a few exceptions. And usually those exceptions are what are called reserved words or keywords in a language. And these are words that already have a particular meaning in the particular language that we're using. And so there is already, right, a function called print in Python. So I cannot create a variable named print. Right? But with these few exceptions, Python gives us a wonderful ability to name our variables. Once we have variables, or we have our data types, often we want to do some type of operation on it. And so operations are very similar to what we have learned in algebra in school. The operators include, say, equals. Equals in the sense of the second one here is testing for equality, and so we will see that in a little bit more in a minute. Then we have the plus, the minus, the divide and times, and these go in the order as we would traditionally understand them from algebra. But these allow us, for instance, to take the number 1 and add it to the number 2, or to take, say, the letter A and add it or concatenate it to the letter B, to get the string AB. Okay. Once we have the ability for variables, and then we have the operators, we can start doing things that are more complex, in our potential program. And then this is where what are called conditional statements come into play. And this conditional statement allows us to perform some type of fork, or have a fork in our code. It's kind of similar to a fork in a road, where I would either go down this path, and check and see if my concentration is equal to 10, as we saw in the earlier slide it is. Then one particular statement would run, this print statement. If my concentration is not 10, that means it is every other option, then I would print out or perform some other set of actions. Okay. And so somebody is asking, Anna is asking if there's a difference between adding and concatenating. That is a great question. And I think that may come down to semantics in the sense that, right, I concatenating is, I think, as far as I know, is much more the adding of strings or variables. I mean strings or words together, right? Where you can add numbers together. What is interesting from a Python perspective is that I use the same operator whether I'm adding numbers or, right, strings. So, good question. Right. So we've seen, right, our basic, our data types, right, our data structures. We've looked at variables, operators, right, conditionals. Now, right, programming languages also have the ability to, right, perform some action over and over again. Right, these are known as loops. In Python, there are two different types of loops. There is what is called a for loop, and that is because there is the keyword for. There is also a while loop, and that is because it uses the keyword while. These are the for and the while predate Python, so they're more computer science concepts. But the take-home message between these two loops is that the for loop, before I ever go into the loop itself, I know, or the program more specifically knows, how many times it is going to run. And so in this very simple example here, we would just be printing out the words that are in this list, and we would print out how long, right, or how many letters are in each of those words. Before I get into this for loop, Python has already understood, right, or calculated that words, the list has 3 elements, and it will loop through it 3 times. In contrast to that, the while loop doesn't know how many times it will be running, and so that puts some extra work, right, on us. And so what we have to do with a while loop is we have to set some type of variable beforehand, right, to a value. The while loop is going to evaluate, right, that variable, in our case 1, I'm sorry, in our case A, and then in the loop itself, I must change, right, the value of this counter essentially, so that at some point it will end, right? It will evaluate so that A is not in fact less than N, and then we can keep going. Okay. If I do not do some type of changing of the value of my A here, then that is where we get that wonderful example of what's called an infinite loop, where that means that I have entered into a loop, but I've given the program no way to ever exit it. And so it dutifully keeps computing and doing whatever it's supposed to do, but it never exits until I, right, close out the program, or say restart my computer. Okay. And then using each of those basic structures, right, or capabilities, I can then, right, put that together into what is called a function. And a function, it's a way to make code run, right, multiple times. Right? So often if I need to perform a task more than once, right, that is, or can be, right, a good opportunity to wrap up something into a function. And so in this particular case here, if I am going to be multiplying numbers in my program over and over and over again, this is a very simple example, right? But if I'm going to be doing this type of multiplication, I can create a function that allows me to multiply, right, and then return the answer each time I use it. Okay. In addition to, right, those different capabilities, right, we also have, right, input and output that programming languages allow us to use, right, or enable us to use. The input and output can be from a file, but it also can be from the network, right? And that in this case is called a socket. So I can read to a socket or the network, or I can write to it just as I can read from a file, right, or write to a file. And then down here, when I am reading or writing to files, they are usually two different types. It's either a text file, right, very similar to like a FASTA file, right, from a bioinformatics perspective, or an Excel file, or there are cases where there are binary files. That means that the data has been saved in a file that allows it to be, say, written smaller, right? In many cases, a binary file is smaller than a text file. And so if you're familiar with next generation sequencing, right, I can take my SAM file and create a BAM or binary version of it, and that makes it a little bit faster, right, to work with because there's less data in some sense, right, to work with. Right? There's less, I can encode the same information, but I can do it in fewer ones and zeros in a binary file versus a text file, right? But the advantage of the text file is that I, as a human, right, can read it, right? Binary files are just ones and zeros, and I have to know, right, where, say, parts of the file start and stop in order to work with it. Okay, so each of those different components are similar, right, amongst almost all programming languages. So if we have, right, those different tools in our belt, how do we use those to write a program? This is a great quote where, and I would say I am as just as guilty, if not more than many, where I get an idea for a program and the first thing I want to do is to jump in and start writing the program. When, as we will see, that is actually the worst thing to do. You want to, right, figure out what to do before you write it, okay? And so when we encounter a new problem or a new task, right, what do we want to do if we think, right, that a script or a program will help us? We want to, I mean, obviously it's understated, right? We want to understand what the problem is, right? I want to be able to plan for how do I attack that particular problem, or how do I think a Python, right, script will help me solve it. And ultimately what that means is dividing that big task, right? We saw, say, data analysis a number of times here, okay? And so if we think about any of these particular tasks, so data entry, right, data analysis, right, reformatting data, right, all of these are these large tasks that we want to be able to accomplish, but they also enable, or they also incorporate a number of much smaller steps. So from a programming perspective, we want to be able to divide that big task into, right, smaller tasks. And then if we need to, right, divide each of those smaller tasks yet again. Right? When we get stuck, right, we're going to work on debugging. Right? If necessary, I would say Google has become, right, our friend with regards to debugging. On occasion, where the solutions that we find won't work or won't work well, right, we can reassess how we might do something. Right? And then that will also mean, right, doing some extra research. But here, when we think about writing programs, right, ultimately what is going to help us is practice. Okay. So this is a neat quote from, right, the physicist Richard Feynman, right? If I can't explain something in simple terms and I don't understand it, that's really interesting when we think about, right? When I talk about, right, understanding our program, right? There are, right, most hard problems are hard because we don't quite understand them, right? So how do we help to understand a problem? It means that we want to be able to try and explain it, right, in plain English. And I know that there are times when I just try and talk through what I'm doing, that it will help me, right, to formulate better, understand better what I'm trying to do. I can do this by, right, writing down my problem, right, doodling a diagram, right, or to tell somebody else about it. Right? With regards to a plan, right, the idea is to, right, create some solution to each of the different steps, or figure out what my, say, my flow chart will look like that solves my particular problem. So the idea is that we don't want to start programming right away. So for instance, if I'm given input X, right, what are the steps necessary to return output Y? Right, this goes back to that black box that we saw a little earlier. Right? What is also interesting to note is that Python at times is described as being self-documenting code. And what that means is that when I write variables and I write function names, that good programming practice allows me to describe each of those very well. And so I don't necessarily need, as we saw with the variable example of concentration, I don't necessarily need to tell me, right, that that is concentration. I don't need a comment to tell me that. Instead, what we do in comments is to explain a little bit of our thinking, especially when there are forks in our code, we're trying to make some type of decision, right? Some information that may not jump out at us when we go to read that code again. Okay? The division, right, of our big task is the most important step of all. Ultimately, we're going to try not to solve one big problem. We want to break it into a number of sub-problems. And then we want to solve, right, each of our sub-problems, right, one by one. And the suggestion here is to begin with the simplest one, right, the one that you know the answer to, and then build up, right, from there. And then ultimately, once I have, right, I'm finished, right, solving every sub-problem, I connect the different pieces, and that's my program. Okay. And so this is one example here is if you're stuck, right, on how to reduce the problem to something simpler, if we think about an example where I want to count or figure out what is the third highest number in a list, if that seems challenging, then what if I simplify it a little bit and I say, what about finding, say, the highest overall number? Right? If that is, right, still challenging, then what about finding the largest of just 3 numbers or just 2? Right? So each of those sub-steps, right, can help me understand my problem better, and then I can build up to, right, this idea of being able to solve, right, a more challenging problem. And then as we talked about, right, it's very odd, right? It's very common, excuse me, to get stuck on, right, writing our software. So by default, I think the common understanding is that debugging, right, takes 75 to 80% of our programming time. And so, right, how do we reduce that, right? We're going to debug our process, okay? But it also means to, right, practice will help us to reduce that somewhat, okay? The idea or the process of going step by step through our code, right, to figure out what went wrong with it is what is called debugging. So the art of debugging is figuring out what you really told the program to do rather than what you thought you told it to do. Okay. Let's see, so I'm going to skip over those. The important thing to understand here is that in debugging and when you're stuck is that you don't want to be looking for a solution to our whole problem. We want to look for a solution to our sub-problems. And so these are the pieces that we're, right, as part of our pseudocode or part of our flowchart that we want to look at individual steps. Okay? And so this is what we'll see that Google, right, will help us with this. And then we talked about practice, practice, practice. Okay. So this is just a little bit of an overview and a very entertaining graphic, right? That weeks of programming, right, can save you hours of planning. Okay. And so what we want to do is we want to apply, right, this formula here where we're going to think about our problem. We're going to outline the steps necessary. Right? This is the pseudocode or algorithm. We're going to convert our pseudocode to an actual piece of software. Then we're going to run and test our program. So with regards to pseudocode, right, this is, right, pseudocode is just another way of creating a protocol, right, or a workflow for the task that we want to create. Pseudocode consists of, right, human readable language, so in essence, right, English, right, language, if that's what I would say, that's what Python is closest to, okay? And in large part, it has 3 different rules with regards to pseudocode. The first thing is that we want to create a sequence of all of our subtasks. And then while we're considering our subtasks, we need to know if there is some type of choice, right? This is where you have the fork in the road. And we also need to know if something is going to repeat or if we're going to need some type of loop to perform our process. And so if while we're breaking up our program into subtasks, we think, are there any choices involved? And then is there any repeating? Right? Then that will help us to create our pseudocode. Other things to consider, and this may be a little bit later on, is like how you're going to store your data, right? If you're going to store your data. I think much of what we're going to use in this series, that will be in essence, right, solved by some of the packages that we're going to be using, such as Pandas. But these are other things that we want to, right, consider. All right, one thing we also need to draw a distinction of is when we are talking about debugging, right? This means that you have written some code, you have tried to run it, and you get an error, right? So those errors can come in, right, 2 broad different forms. The first is called a syntax error. And what this usually means is that you have used either the wrong grammar, or you've misspelled a variable, or you've forgotten something that the language itself is expecting the program to have. These errors, the syntax errors, this is something that a Python debugger can help us with. The logic errors are something that the Python debugger cannot help us with. And so this means that if I have a logic error that the program, right, it's running, but it is not producing the output that I was expecting. Right? And so, for instance, if you are trying to do temperature conversion, as we will work on Monday, if I reverse, right, the division, right, so that instead of multiplying, I'm dividing, right, from the Python perspective, it can look correct, but the output is not going to be correct. Okay? And Melissa, with regards to the Googling, we're going to look at that in a few minutes. That's a great question. Okay. So things have gotten rather interesting in the last few years, as we were just discussing with Googling. I would say for the most part, when we talk about writing software, and this means converting, right, our pseudocode to an actual program, it is not very often that I do this first option. I don't often write all of my own code entirely from scratch. Most often, I will write some of my code, but it will be using packages that are available. That's what we'll be doing in large part in this series. But I would say even more so, what is the most common example nowadays for writing code is to go out and search for the piece that you need. And then as programmers, right, we then combine all of these different pieces into one coherent script, right, that accomplishes the task that we're interested in. Okay. All right. And so with regards to writing a program, right, a program is nothing more than a text file. Right? So when we hear of the words source code, what that really means is a text file that holds, right, programming, right, or it holds a program in a particular programming language. So we can speak of a Python, right, source code. We can talk about a Java source code. Okay? So the code that we see over here is code that's written in Python, right, that sums a number of different integers. Okay? And then I can write it, right, in a simple text editor. Right? This is something even more simple than Microsoft Word. In fact, Word is not a good editor or way to write software. I can use a text editor. I can use an integrated development environment, or as we'll see, right, a Jupyter notebook. Okay. And then Diane is asking about Stack Overflow, and we'll look at that in just a minute. Okay. So this is perhaps, right, the most important, or one of the most important, right, pieces of information that you'll learn today. That code is read many more times than it is written. And so if we think about that for a minute, right, as I am writing my code, right, I write it once and then I debug it. Each time I go to debug it, I am reading my code. If I share my script with somebody, they will read my code. If I put it on GitHub for others to download, they will read my code. So code is read much more often than it is written. Okay. And so when we talk about, right, packages or code, and I talked about gluing the pieces together, right, I can use previous code that I've written. I can use code from, say, other lab members. I can do a strict Google search, which will nowadays most often lead me, right, to the Stack Overflow website, or I can get information or code from GitHub, and or I can import code or packages from a repository. From a Python perspective, that can be the pip, which is the Python, right, index, or Conda, as we've seen. Right? From an R perspective, if you're familiar with R, that would be the CRAN repository. And so this is code that others have made available for us that will usually help us solve part of our problem, but not necessarily, right, all of our problem. Okay. And so this is an example of a Stack Overflow page, which we'll look at in more detail in a minute. And then this is an example of the GitHub website, right? And if you've gone to the GitHub to get the materials for this seminar series, then you're familiar with that. Okay. And so in writing our own code, right, we pick a programming language that we have already done, right? We're going to work with Python. We're going to start with pseudocode, okay? And so what we want to do now is, right, go through, right, an experiment or an example of writing pseudocode, okay? And so we're going to exit out of that, and I'm going to go back over to Jupyter Lab. Now I'm going to go through the Jupyter Notebook here, but I would invite each of you to open up a new Jupyter Notebook. Okay, remember to do that, we're going to go to the Anaconda Navigator. So here I'm going to go to the Anaconda Navigator. Right, so I'm assuming at this point that you have installed, right, the Anaconda distribution. Right, and what that is that allows us to, right, it installs the Python programming language. It installs the Jupyter Lab software that you see here. Right. And so if I bring up this Anaconda Navigator, and I would click on the Jupyter Lab here to launch it, and that's going to take me to, right, my desktop, and then it's going to bring up this launcher that I can then, right, click here under Notebook to create a new Python 3 notebook, and I can tell it's using the Python programming language because over here in the upper right hand corner it says Python 3. Okay. But let's see here. If I click on the Python programming, oh wait, no, that's not what I want. Let's see, I'm going to go into the Intro to Programming, and I'm going to open up the programming example. Okay. And so what I have included, I would say if you're going to open up a new IPython notebook, then actually let me change something for just a minute. What I'm going to suggest is go to the 03_intro_programming folder. So if you downloaded the entire repository, right, this will be the third folder in it. If you downloaded the zip file, then this will be in the zip file. And the reason is that we'll look very briefly, and so if you don't have this, it's not any big problem. Right? You can play with it a little bit later. We're going to look at a Gapminder data set for a moment. Okay. So I'm going to go back into the programming example. Right? And so we've talked about, right, our steps in our process. Right? If we want to, for instance, if we want to start or ultimately try and plot, let's say, some life expectancy, right, versus health over decades from this Gapminder data set, right, how would we go about doing that? Okay. So for those of you who may not know, right, this Gapminder it's a foundation that has or keeps track of, right, data sets from countries all around the world, and it's been keeping track of social and socioeconomic data for the last 60 or 70 years, or that's how far the data goes back. Okay? And so if we open up our Jupyter Notebook, one of the first things we're going to do is take a look at the data, right, in our data set. And so what I have tried to do here is update the code that allowed us to just look at, right, I think last time we were looking at the head command, but that is a Mac and Linux specific command. Okay. So if you're on Mac or Linux, you should be able to run this, and then what it should do is it should show you the first 10 lines of our data file. Okay. And then I would say I didn't get a chance to test it on Windows since I put it together this morning. So if it works, let me know. If it doesn't work, please let me know. Okay. But this, as I understand, is a rough equivalent to the head command for Mac and Linux. And so what we can see here is we have data. It looks like it has 1, 2, 3, 4, 5, 6 different headers or columns. Right, so we have information on country, continent, right, what year the data was taken, right, life expectancy, population, and then the GDP per capita. Okay. Now, if I want to, as we see up here in our made up example, if I want to plot, right, some life expectancy data, okay, over many decades, then right, what steps would I need to perform, right, in order to do that? So let's go and ask so what steps do I need in my program to read data or to plot data, right, from a file? Right, so if you'll go back to the plot, all right, so define some variables. I need to open up my file and read the data in. So I definitely need to know where my data is stored, right? I will need to import, right, my plot function. Okay, so if let's see, here's an example. So import my file, view my data, right, clean it and tidy it, and then plot it, right? So that's 4 different steps, right? Then we need to decide, right, whether I'm going to use a scatter plot, right, with X and Y axis, or a bar plot. Right, this is great, y'all. Okay, so if we take this as a kind of an example, let's go back over to our role here. So I'm going to scroll down a little bit. Right, and so the questions here, right, are very similar to the ones that you all are answering, right? What are the types of data, right, that I want to use or manage? Right? Where is the data going to be stored, right? And basically, what type of data structure do I need? Are there any loops? Are there conditions? And then do I need to write any functions? Okay. So let's see. So I'm going to think about my outline, right? So the first thing I'm going to do is I'm going to open my file. Then once I have my file open, right, I want to read in my data, but I would say odds are, right, I want to read in data from all of the different lines in my file. And so if we start with, say, the most basic form of this, right, instead of plotting all my data, let's try and plot data just from the United States for today. Right? So in order to do that, I want to test and see if the country is the United States. And if it is, then I want to print it out. Okay. And so this will, right, be a starting point And then I would say once we've done this particular thing, right, then we can work on plotting it. Okay? And so if I think about this particular outline from a pseudocode perspective, that pseudocode is the exact same thing as the outline I just created. Okay? And so when we talk about our program, right, I want to figure out how to open up, right, a file. And so the first thing I'm going to do is, let's see, I'm going to go over here and I'm going to create my Python notebook. And then because I'm a new programmer, I'm going to open up a new tab and I'm going to write in here, open file Python, because I want Python help to do it. And I'm going to hit enter. And when I do this, I see that there are only, right, 320 million options for me to check. May I suggest you don't check them all? Right? As I scroll through, I can see that there are, right, options from this, what is it, W3 Schools. There is information from the python.org. Okay, that is the official Python website, so that's a good one. Okay. There is another website called Real Python. This is another very good resource. Okay. And then as we scroll through, we'll see that there are, right, a number of different options for us to check out. Right? But I want to draw your attention to one other thing. What type of file are we going to be importing data from? As we can see here, we're going to be importing data from a CSV file. And so when I'm doing my search, I'm actually going to do a search for open file, or let's say open CSV file, or let's read CSV file Python, right? So that's my task that I want to accomplish. And if I hit enter here, then what we will see is I'm getting some different examples than what I did before. And so if I look at this first example here, this is from python.org. This is explaining the details of the module. And so I'm going to scoot through this, and I see here in green that there is, right, some Python code, and I can tell that this is Python code because there are these 3 greater than signs, and these 3 greater than signs tell me that that was typed in or captured, right, from the Python interpreter. Okay? And so I'm going to come down here and I see that there is this information on how to read a file. So I'm going to copy all of this. I'm going to come over to my Jupyter Notebook and I'm going to paste that information, right, in my code cell. Remember, this is the code cell here. I'm going to clean this up, which means I'm going to get rid of these greater than signs. And then I'm going to get rid of these 3 dots. Okay. And so what I see here is that there is an import CSV that is a module in the Python standard library that allows me to work easily with the Python, with CSV files. I see that it suggests I use this keyword with and the keyword open. Here, I'm obviously not going to be working with this eggs file, so I'm going to type in the name of my file, okay, gapminder.csv. I don't know what this new line is, so I'm going to get rid of that, and I'm going to create this, what's called a handle actually, as this CSV file, right? And so let's see, I see that there is this csv.reader module. And so I'm going to get rid of these. Actually, no, let's just run it like it is. Okay, the only thing I am going to change is that part that was red. Python needs indentation in order to work, and so I'm going to, every time I see this colon here, I'm going to indent once. So here's another colon. And so let's try printing this out and see what happens. Okay, so right in our first step, we've done the search, and I'm able to go through and I can print out every bit of my data. All right, lots and lots of data. Okay, so let's take a look for a minute and let's see how the United States is is mentioned here. Where is United? Let's see. Okay, so here, what the CSV module has actually done is it has broken apart the states, or yeah, I think it has broken apart, or taken the space as a delimiter, which we didn't necessarily need to do, but that's fine. Okay, but what you'll notice here is that we have in a single line of code, right? Let me scroll, let me just collapse that, right? In a single, I'm sorry, not single line, in what is it, 4 lines or 5 lines of code, we have right, grabbed our data, okay? So here I see that there is a delimiter in this empty space in here, so it thinks the space is a delimiter, and that's actually not what we want. So to this example, I'm going to get it. I'm going to make it even simpler. I'm just going to get rid of all the options here and rerun it. All right. And so here, right, I can see that the CSV module is right reading in my data. I don't know what spam reader is, but I'm just going to rename that to reader and then update it over here. Okay. And so in a single search, right, I've been able to figure out how to open up my data. What I want to do is I want to go back to my example here, and I'm actually going to capture, right, my pseudocode, and I'm going to add that, right, to my program. But because it is not actual Python code, right, this is where I'm going to comment each of these lines out. Right? And so the open file task, that's already done. Looping through the file, that is already done. And so I'm going to copy these other pieces down here and move them down. Right? And so in this example, then I need to test to see if a country is the United States. Okay, and so how do I test, right? How do I search or compare? So we know, right, that I can compare, right, information. So let's see, I'm going to do another search here. So I'm going to search for a substring, right, using Python. So search substring Python is my search. And I'm going to hit enter. And when I do this, I'm going to scroll through, and then this is an example where the Stack Overflow is coming up. Okay, Stack Overflow is a website that has many, many, many answers in many cases that address errors that we might find, or programming questions like this. And so this question here, somebody has asked, right, does Python have a string, right, contains substring method, right? And so I'm going to click on this answer, and we can see here that here's the question that was found, right? So it's just a little bit different. Is there a way to basically search for a substring? And the way that Stack Overflow is organized is somebody has asked a question, right? This question was actually asked 9 years ago, right? And then since that time, people have answered that question. And then each time somebody has come across this question, they have the option of either upvoting an answer or the question or downvoting it. So here I'm going to upvote the response, but that's already been locked, so I can't do that. Okay, here I can see that the first answer is there is an in operator that we can try in Python, so we'll try that in a minute. But what I want to draw your attention to are a few different things. The answers here can be ordered by default, they're ordered by votes. I can also order them by what is the oldest answer or what are the active answers. I would say all of them, I think these two other options are relatively new. So at this point, most of them will be ordered by a number of votes. We can see that this was answered a little over 9 or 10 years ago. Okay, and so this may or may not be the current best answer. Okay, so what I will normally do then is scroll down to say the second or third answer and see if there is better code. But what we'll notice also is that this information in the gray here and in the gray here is Python code that I can once again cut and paste to add to my program. And so as I'm scrolling through here, I'm just looking at essentially the first code that comes in, okay? And I see that there is this information on, well, let's go back to our, let's go back to the first reply, okay? And I'm gonna copy that and then paste it back into my program. Okay. So obviously, I'm not searching for, blah. I want to search for United States. And I do want it to be in, in this case, the variable is called row. And so if it is, then I want to print, my row. Okay, so actually let's move this down here, and you'll notice that I had to indent it because that's how Python knows what condition or what part of what code goes as part of this condition. And so I'm going to run this and see if it works. Oh wait, so here I've already printed out, so I'm gonna comment that piece of code out, and I'm gonna rerun it. Okay, and I see that it didn't work. But if you'll notice, there is no red down here, and so that means that it didn't run exactly, but I got no output. So this is an example of what we would call a logical error. Python thinks the program is fine. What happened here was I left off the S on states, and if I rerun it, here I can see that using this code that I have written in these few minutes, I can now read my file. I can now search for and get information that's related to the United States. And I can see that there is, this is the country, the continent, the year, and then we had information on the, let's see, I think it was the population, and then it was the GDP, or no, I'm sorry, the life expectancy, the population, and then the GDP per capita, right? All right, and so let's see. We can see that using my my pseudocode, right, I had 4 lines in it, right? I wanted to open my file. Okay? I wanted to loop through, so I'm actually going to move this down here and see that I'm looping through. Okay? I wanted to test if the country is the United States, and if so, I wanted to print it out. Okay, this was kind of the first start, right, to actually doing our plotting. Okay, but what I want to draw your attention to is look at how close, right, our pseudocode is to our Python code. And so if you recall, right, earlier on I talked about how people describe Python as being executable pseudocode. So here, if I were to read this line, right, I see that there is an open method, right? It is the open, right, is one of those keywords and is contextually colored green. And so that helps to stick out. And then we also talked about how Python is, right, called self-documenting code, okay? And so I don't necessarily need, right, this open statement here from my pseudocode anymore because I see that it's the first line of my code. I'm opening up a file. As I come down and I look at the next part of my file, right, or my pseudocode, right, I can see that I'm going to loop through it. Well, as you become more comfortable with the for loop, you'll understand that that's a for loop in Python. And so I'm looping through my code. And so that, right, we can leave that out or we can take that out if we want. Here, I am doing a test for the United States, okay? And this is the one statement that, you know, is not clear just from, right, our code, right? Why are we doing, right, why are we looking only for United States information? Okay? At this point, it would probably be because we wanted to just simply test something before we go and process all of the data, okay? But we will see in the data analysis with Pandas seminar how we can plot very easily using, right, the Pandas package. But here I would say if I was going to do this, I would get rid of this statement, that print statement there. I would get rid of this loop here. And then I would get rid of this code here as well, because we don't need to talk about printing when we are in fact printing. And so we can see that, right, in our example here, I have 1, 2, 3, 4, 5, 6, 7 lines of code, right, one of which is a comment. And it's very easy, right, for us to understand what is going on, okay? And so in the last, right, few minutes, right, we can see at the bottom here that this is another example, right, of how I might go through if I wanted to, right, if we wanted to use that gap reader, I could also, right, check and see if the first information, right, or I'm sorry, the first item in the CSV file that's been parsed already, right, because we're using the CSV module. I could also have included or used this check to check and see whether the first column, right, as we'll see, Python is a zero-based programming language, so it starts indices with 0. That if I were to check and see if that is United States, then I could print it out, and then you see here that I get, right, the same printout, okay? And so to wrap up, let's look through our little PowerPoint again for a moment. Where is it here? So I hope what we have learned today, right, is that you have become familiar with, right, some of the different programming languages, right, and how and why we need to program computers, right? We've talked very briefly about different scientific packages. This, I hope, will help to understand and communicate with programmers, perhaps bioinformaticians, as we go through this series. Right? You can begin to look at, right, and critique existing source code for your use. Right? That will help you, especially after our next session. And then this will give you some idea of whether or not, right, Python, right, meets your needs. And I would say after the next session, you'll be able to answer that even better. In here, there is some information on, say, Python in general. Let's see, I'm going to hide this for a moment, and I'm going to look in the downloads. And so let's look in the downloads for a minute. So I copied it here, and we can see that there are some other pieces of information. If you're interested in some advanced concepts, there is a presentation on advanced concepts. If this is interesting enough, we could see about doing a seminar on this. This talks about more detailed concepts, but things like graphical processing units and machine learning, and how do you evaluate, right, how long a program may take. But I would invite you to take a look at that. This is another PowerPoint presentation. There is this neat debugging flowchart that is from a gentleman's website. This gentleman, I believe Martin, who created Python for biologists. So there's an example of that. And this can help with debugging. There is also a Git example. So we're going to cover in the reproducible science portion, we will touch upon version control, and this gives you a little bit of an overview of how version control works, but that's also in the advanced concepts. And then I think that is, yeah, that is it. If you have any questions, please don't hesitate to let me know. If there is a way to make this presentation better, to include something you think I have left off, or not include something that I had in here, I would love to hear it. As always, let me put up my email address, and let's get over here. And so my email address is richard.squires@nih.gov. And so you can send me an email if you have any questions or if you're having any trouble with something. I want to thank Brendan again for answering all of these questions. It looks like there are a lot of great questions. Let's see, somebody had a question about the videos. I will be putting those up this afternoon and tomorrow on the bioinformatics NIAID hub. And so if you go to bioinformatics.niaid.nih.gov, then we can talk about that. And then there was a question about, say, other programming languages. We'll cover that more so, I think, in the next one. Specifically, there was a question about R. R is a great language that is used, right, predominantly for statistical analysis. And so there aren't as many capabilities for, say, general computing as there are in Python. For instance, there is no dictionary data structure in R. But we'll talk about that a little bit more on Monday. Anything else that we should talk about, Brendan?
Yeah, maybe a couple points you might want to touch on if you got a couple minutes here. Sure. So, why is it a good idea to use the Anaconda distribution for this Python? You know, I think Macs that have Python installed automatically. However, it's the system Python, and so Anaconda is nice in that it separates that Python away from system Python. And so, but more than that, right?
Yes, that's a great question. So first of all, right, we have to have the Python programming language installed in order to write Python code and have it interpreted. You can use the Python that came with your computer, right? So as Brendan mentioned, Macs come with Python. It uses an older version, a version 2.7 of the language, which is a little different. But that I don't know if you would need. I would suspect that you would need, say, admin privileges to add packages to it. Although it's been a long time since I've actually tried using the built-in Python to do that. But the question, or I would say one potential problem there is that if anything were to go wrong, right, you have in essence broken the programming language that the OS is depending on, right, in some respect. The advantage of the Anaconda distribution is that it installs the current version of the programming language. It installs the Jupyter software. I would say more importantly, it installs the Conda installer, which allows us to very quickly and easily update the programming language, right, the different packages. With the Anaconda installer, as we saw in Monday's presentation, I can create environments. And so if I want to create a program in Python that for some reason uses an older version of the Python programming language, so if I need it to run, say, version 3.5 of Python, I can create an environment using the Anaconda distribution that has just the version 3.5 of the programming language, as well as specific versions of any of the packages that I need. And then that would never change unless I go in and update it specifically, or if I get rid of my Anaconda folder, right, and then have to reinstall it. But it allows for us to easily install the software and packages. And then as we saw on Monday, it also allows us to easily install other software, right, using the Bioconda package as well.
This could be kind of an extensive question, so I don't know what to be more specific, but you are going to come up with potential differences when using Windows versus a Mac, right? And someone asked the question, why would it matter? We're writing in Python. And so if you could touch on, that the sort of the file structure of the two different operating systems comes into play while you're trying to access files and things like that. And things like Bash isn't available on Windows unless you do some other stuff. Right. So.
Yeah. So the Python will run, as we saw. It'll run on a Mac, or it'll run on a PC, or it'll on a Windows machine, or it'll run on Linux. Right. Actually, it'll even run on smaller computers like a Raspberry Pi, if you're familiar with them. It'll run on almost anything. The big difference between Mac and Windows is that the way that the operating system is organized, right, and how you locate files is different. And so you can write Python code that uses the operating system or the OS module, and it does it in a platform agnostic way. So I can say that I want to go to the desktop and open a file, and I can write Python code that doesn't matter, or it doesn't care whether that is on a Windows machine or on a Mac or on a Linux machine, because it will automatically determine, right, where the desktop is. But the code that I was working with earlier, right, where we used the head command to look at the very beginning of our file, the head program is a Unix program, and that by default is not included on Windows. You can, right, install the Linux subsystem for Windows, right, depending on your institute, whether they allow that or not. And then my understanding is that in the not too distant future, that Microsoft is talking about making Linux more of a parallel system to Windows by default, which will be really interesting. So if you go into the Windows Store now, you can search for Linux or Ubuntu, right? Ubuntu. That is a version of Linux, and you can install that side by side with your Windows, and that would include bash. And the advantage of something like that is that then you can take the code, right, that you're writing on your Windows machine, right, that also has those Linux portions, and I can drop it directly on the compute cluster, and it will run, right, should run just the same. Right? And if somebody else needs other information or something, then feel free to just send me an email.
Okay. Thanks, Mark.
Well, thank you, sir. Well, thank you all. And let me know, and we will talk to you. I look forward to talking to you. We're going to go over an introduction to the Python programming language itself on Monday. And as always, please check the bioinformatics portal. .nih.gov. So bioinformatics.niad.nih.gov. And there we will have updates to the seminars. So we are adding seminars on, I would say, a weekly basis, not quite a daily basis. But if you look at upcoming events here, you can see the different upcoming events, right? And these are all available at no cost. And then under training resources, this is where we have materials from previous versions of this seminar series, as well as information on, say, next generation sequencing analysis, phylogenetics, structural biology, say, in biostatistics, etc. So please take a look, and then we look forward to talking to you again on Monday. Thank you all.